So far we have derived an expression for repulsive force between two interacting surfaces. When we say interacting surfaces, it means that there is an overlap of electrical double layer, and the expression that we have been able to obtain is this, that is the excess pressure or the force per unit area with which the particles or the two surfaces that we are considering, that is this and this, are pushed apart as a result of overlap of electrical double layer is given by this. F r is equal to 2 kBt n infinity cos hyperbolic Z e psi at h by 2 divided by kBt minus 1, and because we can express cos hyperbolic x as a series expansion in this form, instead of cos hyperbolic x minus 1, I can substitute for cos hyperbolic x minus 1 is equal to x square by 2 factorial, and I can neglect the higher order terms. So, if I do that, in the end the expression for repulsion becomes something like this: 64 kBt n infinity gamma naught square exponent of minus h divided by kappa inverse. That is what we have derived so far. Now, if you look at this expression, if we what we would like to do now is to look at a case where the distance of separation between the two plates is fixed, that is h is fixed, and because we know that kappa square depends on the permittivity, temperature and the ion concentration in a particular way, therefore, kappa varies as n infinity to the power of half, right. Kappa square goes as n infinity, therefore, kappa varies as n infinity to the power of half. So, that is essentially is, so if this is kappa, therefore, kappa goes as, so I can, if I take square root on both the sides, essentially kappa goes as n infinity to the power of half. So, I can so this is a constant for a given, because if you are working at a given temperature, this is constant, and if the surface potential is fixed, this gamma naught square would also be fixed. Therefore, I can write the expression for the force of repulsion as some constant C1 times n infinity exponent minus some constant multiplied by n infinity to the power of 1 half. Therefore, from this expression what we can conclude is that the force of repulsion decreases with increase in electrolyte concentration between the two surfaces compared at same distance. Okay. That means, for a given distance, because you have there is a pre-exponent term and there is an exponent term, because of the fact that this decreases much more drastically with increase in the electrolyte concentration. Therefore, the overall effect is essentially governed by this term. Therefore, the force of repulsion decreases with increase in the electrolyte concentration. And the other point that we can make is that the addition of the other way of saying this same point would be the addition of electrolyte to a dispersion in many cases is known to induce the coagulation of colloids. That means, if you have the particles nicely dispersed, the addition of electrolyte like salt, for example, right, it gives rise to the coagulation or aggregation of particles that arises because of the fact that increase in the electrolyte concentration leads to a reduction in the repulsive forces, which will make a colloid to go from a stable state to a destabilized or a unstable state. Since we know that the potential is given by the force times distance through which it operates, for a change or for an increment, the change or the increment in the potential arising from a change in the separation distance, you can actually calculate by knowing f of r. Therefore, because d phi of r goes as minus f r times d h, therefore, one could integrate this expression to obtain an expression for the potential of repulsion between the two charged surfaces, and if I use the boundary condition that the potential becomes 0 when the distance of separation is very large, right, at a separation distance which is much larger than K inverse, or if you consider the distance of separation to be very high, the force of repulsion would be 0. Therefore, phi of r essentially goes as 64 kBT n infinity kappa inverse is a factor that comes when you integrate this term, and of course, you are going to have the exponent minus h by kappa inverse term intact. So, therefore, now what you have is that so if you look at n infinity here, right, n infinity goes as okay, let us go back to the previous expression. So, so you have a kappa inverse here, right. So, therefore, you had kappa which goes as n infinity power half, n infinity power half, and you have kappa inverse which goes as n infinity power minus half. So, because you have n infinity here, right, and kappa inverse goes as n infinity power of minus half. Okay, so, let me just quickly. Okay, so, you have n infinity to the power of 1, that is this term, and kappa inverse goes as n infinity power minus half. Therefore, overall phi r, the energy of repulsion or the interaction potential goes as some constant times n infinity to the power of half and exponent of minus C2 some other constant times n infinity to the power of half, and again this expression is written for a given separation distance. Of course, this expression is again valid when the distance of separation between the surfaces is large. Okay. Again the same conclusions can be drawn that the potential energy of repulsion decreases with increase in the electrolyte concentration because of a strong dependence of the exponential term on the concentration of the electrolyte that are being considered. Okay. So, we have been able to derive this expression for the overall potential or the total electrical double layer potential. We were able to do it, or it was possible to obtain this expression because of the relatively simple approximation for the potential at the midpoint. Okay. So, we said that it is not the potential at the surface, but the potential at the mid plane. Okay. The potential at h by 2 is what governs the electrical double layer repulsion, and of course, we did use a superposition approximation to say that psi at h by 2 is equal to psi 1 plus psi 2, right. So, we essentially used this approximation to obtain how the phi of r quantitatively depends on the several parameters involved. Okay. However, a general method for the evaluation of the potential energy of repulsion, it was derived by, or it was put forward by Verwey and Overbeek, in which a numerical simulation was used to capture how does the potential energy of repulsion varies with separation distance for any charge stabilized colloidal system for a very general case. Of the conclusions from these numerical integration procedure are that the potential energy of repulsion may extend appreciable distances from surfaces, but its range is compressed by increasing the electrolyte concentration of the system. Okay. So, when we say that the potential energy of repulsion can extend to appreciable distances from the surfaces, we are talking about distances of the order of kappa inverse or less, okay, or of the distances of that order. And however, the the strength of the repulsion is reduced or compressed, or it is decreases by increasing the concentration of electrolyte in the system. The second point is the condition under which approaching particles first influence one another are at large separation distance, for which the approximate relationship is given by this. So, therefore, the general solution that has been developed by numerical integration, it kind of reduces to this particular expression when we are considering a moderate overlap, or when the overlap is such that the distance between the particles is sufficiently larger. The sensitivity of aqueous hydrophobic colloids to electrolyte concentration is due to the dependence of the interparticle repulsion on this concentration. So, there are several systems where lyophobic, that means the colloidal particles which do not disperse well in solutions are considered, and the colloidal stability of such particles and the dependence of their stability on the electrolyte concentration is kind of captured by this particular theory. Okay, so, that is about the overlap of electrical double layers and how does that manifest into the repulsion between the particles. So, now we will move on to looking at colloidal interactions in charge stabilized suspensions. So, what we have is a schematic 1 and 2 in which what is considered is you have a dispersion of negatively charged particles and a dispersion of positively charged particles in a fluid medium. And whenever you have a system of charge stabilized colloidal system, so you have to think about the attractive interactions between the particles, and that comes from the contribution of the van der Waals forces, which were discussed in module 2, and the repulsive interactions which come about because of the overlap of electrical double layers, which has been discussed in this module or the module 4. Okay. So, in such a system of charge stabilized colloids, the total interaction as a function of separation distance d is given by the summation of the van der Waals contribution and the electrostatic or the electrical double layer contribution. And this fact that the total interaction energy is the summation of the van der Waals forces and the electrical double layer forces is what is called as a DLVO theory, which is named after Derives, Landau, Verwey and Overbeek, and this theory was put forward to explain the stability of charge stabilized colloidal dispersions. So, and what you see here is a plot of how the DLVO potential or the total potential in a charge stabilized suspension scaled with thermal energy, how does that vary as a function of separation distance. So, you have repulsive contribution that comes from the electrical double layer effect, and the van der Waals contribution that comes from the van der Waals, the attractive term in the expression, and the continuous line that is drawn here is the DLVO interaction. And so, because you have electrical double layer repulsion and van der Waals attraction, which are of opposing tendencies. So, whenever you add up this term, you are going to have a maxima, right, and depending upon the extent of this maxima, okay, what is the what is the energy that is required for what is the energy that is required to overcome this barrier, so that the attractive interactions become dominant. This is what is called as a energy barrier for aggregation. So, typically when this energy barrier is of the order of several tens of kBt, one could say that such colloidal dispersions of charge stabilized particles are stable to aggregation, okay, and one could manipulate the strength of this energy barrier by manipulating by playing with several conditions, which we are going to discuss in a while. Okay. So, the contribution of individual interactions, that means the contribution of the electrostatic interactions or electrical double layer interactions and van der Waals interactions to the total potential depends on the particle geometry, whether we are working with spherical particles or planar surfaces, okay, or elliptical particles. Okay. So, it depends on the particle geometry, and when the particles are not isotropic, that is non-spherical, okay, any case other than this, it turns out that what is also important is the orientation effect. That means, whether in the case of ellipsoids, if are the particles when they approach, are they oriented in this particular fashion, or are they oriented in the tip fashion, or are they oriented tip to the side. Okay. So, therefore, depending upon the orientation of the particles, the individual contribution could vary. The individual contribution also depends on the surface charge, what is the charge density on the particle surface, the concentration of the electrolyte in the solution, and the chemical composition of the particles, and many other factors as well. Okay. So, for a planar surface, we have derived this expression for how the potential varies with separation distance, and this expression again we have derived in module 2, that comes from the van der Waals forces, where kappa is given by E square divided by epsilon kBt summation I z I square n I infinity. Okay. So, now if you take particles of a particular geometry or a given geometry, in this case if you look at planar surfaces, if you look at the phi net or the phi total or phi DLVO, you can say that the total potential depends on several parameters. For example, temperature, because you have the temperature term in the electrical double layer repulsion. Therefore, one could play with the temperature of the solution and then modulate the total potential. It depends on the permittivity as well. So, if you have kappa inverse here, and kappa inverse depends on again temperature as well as permittivity. So, therefore, you can disperse particles in fluid of different permittivity and then manipulate the total potential. The chemical composition of the particles also is important, because the chemical composition dictates what is the Hammaka constant of the particle under consideration, and the surface charge, whether the charge density is high, low, okay, which will directly affect what is the electrical double layer repulsion, and finally the concentration of electrolyte as well. Okay. So, we will look at a particular case and look at how each of these parameters are going to affect. So, what we are going to look at is essentially plotting this expression. Okay. What we are going to do is we will consider a case of planar surfaces, so for which the total potential is given by this expression, right, and we will look at the effect of the effect of variation of Hammaka constant. Okay. So, what we will do here is that we take a particular case. So, we are going to plot phi net, which is scaled with kBt, and we are going to plot phi net as a function of separation distance d. Okay. Of course, these expression is for flat blocks or the planar surfaces, and these plots that you see here, they are actually drawn for different values of A212. That means, this is A212, that is, this is the blocks of similar chemical composition 2, they are interacting via medium 1. So, therefore, and they are plotted for a constant value of k, that is k is 10 power 9 meter inverse. That means, the concentration of electrolyte is fixed, concentration of is fixed, and they are also plotted for a case where psi naught is equal to 103 millivolts. Okay. And of course, the temperature is also fixed, and the medium 1 is medium 1, that is a medium, okay, of fixed epsilon, right. So, therefore, if you look at the contribution of the electrical double layer and the van der Waals forces, what is kept constant in this plot is that the electrical double layer interactions are kept constant, and the only contribution that is being varied is what is the van der Waals contribution. So, therefore, what you will see is that so this is the dotted line that you see is for the case where A is 2 into 10 power minus 19 joules, and this is for 10 power minus 19, and this is for 5 into 10 power minus 20, and this is for 2 into 10 power minus 20 joules. Therefore, as you move in this direction, Hammocke constant A increases. Okay. Now, when A increases, that means to say that for a fixed electrical double layer interaction, when A is increasing, what happens is the van der Waals contribution becomes more and more dominant as A increases. Therefore, there is some energy barrier for aggregation, okay, of the order of 3 kBt when A is 2 into 10 power minus 20 joules. However, when the value of A increases to 2 into 10 power minus 19 joules, that is 1 order of magnitude increase, you can see that the overall interaction is always attractive, right. If you look at this case, okay, if I draw this line, right, you can see that the overall interaction in that case is always attractive. That means, for a given separation distance that we have considered, okay, the total interaction is always attractive. Therefore, this method gives you a way of manipulating the overall interaction between the colloidal particles by varying the Hammocke constant of the material being considered. Okay. So, so now what we can do is we can consider a case where again you have phi net D is phi electrical double layer plus phi van der Waals. Okay. So, what is done in this case is A naught is fixed. Okay. There, because A naught is fixed, the van der Waals term is fixed. That means the variation of van der Waals force of attraction with distance is fixed, and also fixed is the concentration of the electrolyte. Kappa is 10 power 9 meter inverse, and the temperature is also fixed 25 degrees centigrade, and the medium is also fixed, therefore, epsilon is fixed. So, if you look at electrical double layer interaction, when the temperature, medium and kappa is also fixed, phi electrical double layer depends on what is the surface potential. Okay. So, in this particular case, what is varied is the surface potential is varied, and it is varied over a wide range all the way from 103 millivolts to 257 millivolts. Therefore, you are increasing the surface potential in this particular fashion. So, therefore, with increase in the potential, so what will happen is, as expected, the electrical double layer interactions will become more and more dominant. Therefore, if you look at the repulsive contribution would increase as you systematically increase the electrical double layer contraction. Therefore, for a fixed van der Waals force of interaction and for a given salt concentration, you can manipulate phi net or the total interactions between charge stabilized colloids by manipulating the surface potential, and with the increase in the surface potential the magnitude of repulsion would increase. So, the third way of manipulating the total interaction potential is by varying the electrolyte concentration. So, in this case phi electrical double layer plus phi van der Waals, okay, that is phi net or phi DLVO, and again the van der Waals contribution is kept constant here because A is fixed at 2 × 10 ⁻³ 10 millijoules, and psi naught is fixed, that is the surface potential is fixed at 25.7 millijoules, okay, that is the limit of the low potential case. And so, in this particular case what you have is, this is drawn for two spherical particles of radius 100 nanometer. That means, we are considering two spherical particles, okay, whose radius is 100 nanometer, and we are looking at the variation of total potential as a function of separation distance. And what is changed here is, if you look at the plot, there is different values of k that is mentioned, okay, the different values of kappa, and that is achieved by adding different concentration of electrolyte into the system. So, if you move in this way, kappa, the value of kappa is increasing. Therefore, if you move this particular way, kappa inverse is increasing. Okay. The fact that the kappa inverse is increasing, that means, if you increase in this, if you go in this concentration, the concentration of electrolyte decreases, right. Kappa is increasing, right. Yeah. Okay. So, the concentration of the electrolyte decreases. When the concentration of the electrolyte decreases, that means we are, if you look at the total contribution to the interactions, so the repulsive interactions are becoming more and more dominant because the electrolyte concentration is decreasing in this particular way. So, therefore, a system such as this, so therefore, just to conclude, a system such as this will have a higher concentration of electrolyte, okay, higher concentration of electrolyte. Therefore, what will happen is the electrical double layer contribution to the total potential is weaker. Okay. However, if you look at a case like this, okay, the kappa inverse is larger, that means the electrolyte concentration is lower in this case. Therefore, the electrical double layer contribution becomes significant, and therefore, the overall interactions, if you look at, there is energy barrier that comes into picture, right, because if you look at this scale, this is kBT at 25 degrees centigrade. So, therefore, there exists a energy barrier for the particles to aggregate, and that happens when the concentration of the electrolyte is lower. However, if you increase the electrolyte concentration, the van der Waals force has become dominant, and the overall interactions, if you look it up, it is positive. Okay. So, with that we come to the end of module 4, where we have been able to look at a system of charged particles. So, we started with looking at the origin of surface charge, then we looked at the concept of electrical double layers, then we discussed electrical double layer models. Okay. So, followed by we looked at overlapping double layers, okay, and followed by that we talked about the colloidal interactions in charge stabilized dispersions, namely the DLVO theory. Okay. So, yeah, so that will be it in this module.